Okay, guys, so let's look here at the problems and just make sure the microphone is on the right side of the computer. There we go. So let me know if you can hear me properly. I think here everything is set up properly on my side. So let's see, on the first problem for this review of fundamental engineering for fluid dynamics, I'm going to do like in dynamics. I'm just going to go through problems and I'm going to describe them, okay? So, so basically fluids, the only thing I want to say before I start is that fluids basically is based on two equations. So motion of forces equals to ma, and then the other one, which needs to, the other equation, we needs to be able to relate the type of fluid to the equation summation of forces equals to ma, and that is the shear equation, saying that the shear stress is equal to the velocity profile divided by the layer length, okay, the layer height. So basically you probably see that curve that looks like a side parabola this way, that shows the shear, okay, that's it, basically describing the equation. So in this problem, what is the pressure at a point 1,800 feet below the surface of the ocean? Now you have these choices. So the equation you need to know is that the pressure is equal to rho GH, okay? Or like they give in some fluid textbooks, gamma times H. So rho is the density, G will be the gravitational constant. So this is gamma H actually by changing the units, by changing here the units. Okay, so this gives you an answer of 8,000. And here you also have some type of responses. Okay, all these problems correspond to the problems I gave you. So you see on the problem statement, they give you the equation. And this will be, you need to pay attention here to the units because the trick is to realize that they ask you this in PSI, which is pound per square inch, so inch square, and they give you the data in foot square. So you need to do the unit transformation. Here they give you the gamma, which is gamma H, okay? Second problem is kind of similar. For the barometer shown in the figure, what is the atmospheric pressure if the height is 20 centimeters and the density of the fluid is 13,550 kilograms per meter cube, and the density px, so inside the vacuum here, basically is 0. Okay, so you need to find what is the pressure here. So again, here they give you the equation, the P atmospheric, this one would be equal to PA. So would be PA would be over here, PV plus rho H. Okay, so here the trick is to realize that when you have the same line over here, so the pressure here and here should be the same. So the pressure at this point should be equal to what? Should be equal to the atmospheric plus the pressure of the fluid pushing over here down. So basically that's why we're over here. P atmospheric per rho GH, where this will be the H over here. So it will be, so if PV is 0, if the one is 0, then becomes P atmosphere equal to rho GH, and we get about 26.6 kilopascals, which I guess is one of the answers. So it should be answer B. All right. So basically here is just direct applications on how to apply the equation that they give you. All right, the other one is another manometer, and this one is exactly the same thing, okay? So basically, again, if the fluid, this one was at AA, the pressure is the same, okay? So what should be the pressure at point A? So it should be pressure at point A is equal to PA. All right, this one, if you look at this one, PA equal PA plus all this one. So PA equal to P atmosphere, the one pushing up, plus all this one over here. Okay. So that's basically what we're gonna over here. So that P1 equal P atmospheres. We do the substitution. All right. So yeah, let's be careful here. 1 second. Maybe let's look at this. Yeah, let's look at the solution once more. Because let's see what we need to find. In the figure, what is the absolute pressure PA in vessel A? So what is PA? PA is the point over here. Okay. So this type of problem, like I said before, you need to start from one of the ends. So let's say the pressure here is the same as here. Okay. So the pressure here we have what? PA. That would be, this one will be equal to P. So it will be equal to rho GH plus rho atmosphere. But also this pressure here, which should be the one, should be equal to PA plus this fluid here. You see, this is a different fluid, rho 1 H1. Okay. And you see, yeah, here we go. You see the different fluid. So, okay, let's see if this time we can get it right. The pressure at this point AA is the same. So let's look first on the right-hand side. The pressure here should be equal to what? Is the P atmospheric, this one plus the height of the fluid. And this one will be the P1 plus the height of the fluid over here. Okay. So basically, if we equate both of them, we get this equation. And if we solve for P1, which will be PA, we get P atmosphere plus rho of the fluid M, GHM, which will be the darker one. And 1 H1 would be this one here that's almost cannot be seen. Okay. So once you do the units, the substitution, being careful with the units, you're going to find out that the P1 should be equal to 15.85 PSI. But again, here you need to be careful again with the units because they give you all this in cubic feet and they ask you the response in inch square. All right. All right, fourth problems. Water flows through a 20 centimeters diameter pipe. If the critical Reynolds number is 2300, what is the maximum value of the average velocity for which laminar flow can be assumed? So you might know that depending on the value of the Reynolds numbers, you can determine if the flow is laminar or if it is turbulent, okay? Generally, small values of Reynolds numbers we say that is laminar, and large numbers would be that is turbulence. So this is for water, so I'm not that familiar for water, but for air, I think the Reynolds number above 10,000 basically means turbulent air, and under 10,000 is laminar flow. But for water, the densities are larger. So the larger the diameter of the tube, okay, the more water, so probably would be laminar. If the smaller it is, it will increase the velocity, and probably the flow will be then turbulent. But basically, they tell you to be laminar with this density. So basically, the Reynolds number equation will be the velocity times density times d divided by mu, okay, which basically is the equation given over here. All right, or if you simplify this mu over density, that's the viscosity, so you get velocities times diameter divided by viscosity. All right, in this problem, let's see, they give you the density, or we need to know the density of the water, as well as the dynamic viscosity of the water, okay, which would be this ratio here. So basically, we'll calculate over here, this will be Reynolds number, or you solve here for V, Reynolds number times mu divided by rho d. So 2300 times the density times mu, divided by the density, so viscosity density, 1000, and d for this case is 20 centimeters, so it will be 0.2. So the velocity will be 0.00292. Okay, and these two values were basically given to you. All right, let's go to problem 5. So again, now this is for air. So it's a similar problem. What is the coefficient of drag for a flow of air? And they give you the density and the viscosity of the air over a flat plate that is 93 centimeters long if the velocity of the flow is 86 meters a second. So again, this time they give you they give you the equation. So what is the coefficient of the drag flow? Okay. So let's see what they give you here. So you see here, depending if the flow is on the characteristics of the flow, so basically it would be laminar or non-laminar or turbulent, you're going to have a different expression to calculate the CD, which is the drag coefficient. So the first thing we need to do is to find the Reynolds number using the same equation as before. So Reynolds numbers will be rho divided by mu, velocity of the flow times the length of the plate. Okay. So in this case, we get 1.225 that was given over here, divided by the 1.810 to the minus 5 times the velocity of the flow, 86 times the length of the plate, which is 93 centimeters or 0.3 meters. And we're going to get the Reynolds number of 5,443 10 to the 6. So we see it's going to be a turbulent flow. So we need to apply this equation here, which will be CD will be equal to 0.031 divided by the Reynolds numbers to the power 1 to the 7th. So if you do the numerical application, you get that CD equals 3.381 10 to the minus 3. Okay, this one is a bit more difficult because you need to know the head loss equation, but it's given to you in the book. So water flows through a 17 centimeters diameter horizontal pipe, and you know that the Stanton friction factor, okay, which is the letter F, is equal to 0.017 at a rate of 0.034 cubic meters per second. So this is like the volumetric flow rate, okay? So what is the frictional head loss per meter of the pipe length, okay? So you have all this equation here. All right. So basically what you need to find is the H, all right? So you know the F, so it's F equals FL over D, V squared over 2G. So basically, this equation, I know that the velocity will be equal to what? To the volumetric flow rate, which is 0.34 divided by the area. You just need to look at the units. What do you need to divide this by in order to get units of velocity will be the area. So we have Q, 0.34 cubic meters per second divided by the area of the tube. That will be pi over 4 times the diameter. Okay, so it would be pi r squared. If it was the radius, it would be pi over 4 times the diameter squared. You will use the diameter. So we will get the velocity to be 14.98. So now we can substitute directly into this equation, 0.017 times 1. So this is per unit meter. So this is 1 over the diameter would be 0.17. So basically this L over here, you could move it down here. So you will have an H of F over L per meter of pipe. Okay, so I put, or here what I put, instead of saying per unit of unit length, I just put 1 meter. Okay, but it would be the same thing as moving the L on this side of the equation. Okay, and you leave this one as 1. So really this should be H over L, and then you have here just 1.14 without the M, once you substitute over here the values. So really the answer should be 1.14 and no 1.14 meters that they put over here, because they ask you to find this per meter of pipe. Okay. So anyway, I think that I put the 1 in order to match the units, but if you ask me, I would have divided here by L. Anyway. Okay, so this is a problem that can be actually from fluids or can also be from thermodynamics. All right. So what is the pumping power required for the system shown in the figure? Neglect friction in the pipes. So basically what you need to figure out is what is the power of this pump over here in order to be able to pump the water from, let's say, a lake to a height of 120 meters, okay? To a container which is ordered. So this is what is known for incompressible flow, means that the density remains constant, right? So this is what is generally known as the Bernoulli equation, even though they call it, but they call it also the energy equation. And this is the pump power, which is basically Q is the volumetric flow rate, and they give you the equation. But here, I mean, this is just to substitute the equation, but I make this more like from thermodynamics, where, for example, if you apply the first principle of thermodynamics, and this will be the pump becomes an open system, okay, where you have mass coming inside this open system and leaving this control volume system, okay? So imagine the pump, you have, so there's no heat, you need to work, you need to provide work, so that would be the W. There's a flow coming in, H, okay? H of whatever is coming in, and it will be an MH of whatever is coming out, okay? But in this case, we're not interested about the H, which the one I'm talking here, this is not MGH as a change of height. This is the enthalpy, all right? So if we look at this equation, we have here the 0, 0, so about the H, the Z really will become the height, that then becomes the H, sorry for the notation. So this is enthalpy, and now this one will be height. So if we take this point as reference here for the potential energy, so H equals 0 here, then at the inlet, this will be 0, and MGH at the end will be this one over here, okay? Where M here, M dot, because we're talking about an open system, is the mass flow. So generally units of this will be kilograms per second, but also the definition for this is rho AV, which is the same thing as Q, okay? This is what they use in thermodynamics for the volumetric flow rate. So you see over here, this equation becomes rho AV is replaced by QGH. So once you substitute, the density is 1,000 of the water. Volumetric flow rate, you see, is 50. All right. 9.81 for the density, and the height is this. So if, let's say, if the pump was 100% efficient, there were no losses, the amount of power that this pump should have is 58,860 kilowatts. But because they tell you that this pump is only 90% efficient, okay, basically what does that mean? That you need to multiply this value here by 1.1, or basically the out here, the efficiency is whatever you get out by whatever you put in, okay? So if it's 90% efficient, means that you need to put an extra 10%, which is the same thing as divided by 10. So at the end, the total power of the pump should be 65,400 kilowatts, which is probably one of the answers. 65,400 kilowatts. Problem 8. So what is the Mach number of a fluid stream flowing at a velocity of 370 feet per second? Where this is the C, this is the velocity of sound, okay? 1,880 feet per second of speed of sound, okay? So they give you the equation. Again, this is a thermodynamics quantity, KRT, where K will be the gas constant, R is the universal gas constant, and T is the temperature or ratio of specific heats. It's the same thing. Generally, for aerodynamics problems, they use the letter gamma. So the Mach number is also equal to the actual velocity divided by the speed of sound. So basically, the Mach number over here will be, okay, the equation they give you over here, velocity divided by speed of sound. So very simple problem. So you divide the 370 by the 1080. So basically, if an object, let's say it's an aircraft flying at 3,070 feet per second, that is equivalent to a Mach number of 0.342. Okay, problem number 9. For steady flow of a compressible fluid in the expander shown in the figure, what is the density at the exit section? So basically, this is like the Venturi effect, but this one is the reverse. You start from something small to something larger. So what should happen to the velocity of the flow? It should decrease, no? As is shown over here. The fluid will remain the same. So for steady flow of a if compressible, so if it's compressible, it means that the density actually from here to here can change. For a steady flow of a compressible fluid in the expander shown in the figure, what is the density at the axis? So you see, that's what I was just saying. If they say it's compressible, that means that the density is not constant, meaning that the density here is not going to be the same as the density here, and that is exactly what we need to find. Okay, so again, there's a bunch of equations here, which this is just an extract from the FE textbook that you can have. But here I also work out the solution. So here, this is again a fluids problem, but also a thermodynamic problem. So this becomes an control volume system or open system for which there is conservation of mass. So the amount of mass coming in is equal to the amount of mass coming out, which is what I put over here, and 1 equal 2. Using the same equation as before, AV will be the volumetric flow rate. So rho AV going in, rho 2 A2 V2. So we solve for the density at 2. We have rho 1, ratio of the two areas times the ratio of the two velocities. Okay. So this will be, what will be the area here? Will be pi over 4, this value to the square, pi over 4, this value of the square. So the pi over 2 probably will cancel out. So we can just put this one becomes the ratio of the diameter square, and this just be unchanged, the ratios of the velocities. Okay. So once you substitute, what do we get? 200 given to you. The ratio of the ratios would be, so 10 squared divided by 15 squared times 20 over 14. And if you do this calculation and track the units, you get 126.98 kilograms cubic meters. So basically, answer D after rounding off the answer. Okay, so in this problem, this is again impulse and momentum. So yeah, this one is more a fluid than a thermodynamics, but again, it could be solved. So let's read the problem. Water flows into the T shown. What is the average velocity of the water entering the T? So basically here, this is based on the conservation of mass. So the amount of water coming in is to be equal to the amount of water coming out. So the good thing is that here the two radius is the same. So basically it would be the same amount of water coming out this way than it would be this way, okay? So the amount of water here, we know the mass flow. Okay, so we need to find the velocity. We know this cross-sectional area, and we know the density. So as before, what would be the amount of water coming in? Would be rho AV1. So we know M, we know rho, we know A, so we can calculate V1, okay? M is given, rho is given, and A, this would just be pi over 4 diameter squared. So we can find the average velocity coming in here would be 3.557. So water flows into the T shown. Where is the average velocity of the water entering the T? Okay, so I thought we're gonna have to find this one coming out, but it's just this one coming in. So the answer is 3.5367, which will be this one. But again, the answer could be what? Find the velocity coming over here. So what would that be? Would be rho AVA. This one is to be equal to 2. These ones out because these ones are the same. All right, it will be rho A2, V2 density will be the same, and you can solve for knowing V1, then we can solve for V2. So this is a continuation of this problem. What is the magnitude of the force required to keep the T stationary? Okay, so I do here the figure. So basically, when you have the fluid here, it's going to push on the wall over here. So you're going to need one force over here, F of X, in order to keep from moving. And now what is good over here is because since these ones have the same area, basically the force produced on top will be the same as this one here. that is because we neglect the effect of the weight or the gravity of the water, okay? So, so the good thing is that we don't need to find these forces over here, Vy, because they are the same. But if those two openings were not the same, then it would be, the problem would be a little bit more complicated. So basically what we need to find out here is that if you put water here, what would be the force you need to do with your hand, let's say, in order for the T here section not to move anywhere. So basically it's conservation of forces. So F of X would be equal to what? Ma. So if you think about it, Ma is what? M dV dt, but this is dm dt times V. So this is kind of the same, okay? And I think they give you the equation anyway. They give you the, yeah, because this is rho AV2. This becomes the same thing because they give you the volumetric flow rate, but I think it's easier to look at it this way. Okay, so what is momentum? All right, momentum is force is mass times velocity per unit time would be mass flow times velocity. So it looks like they give you the mass flow over here, 1.6 times V1, which would be the velocity we calculated before, would be 3.5367. That gives you 5.658. Again, this force here should be equal to 0. So you have Fx here, if you look at the free body diagram, will be equal to what? To M1 V1, okay? But also pay attention to the units. It would be like force equal to Ma, okay? Which is M dV dt. So it would be, this is the M dt over V. So you could move the dt, let's say, to this one, and you will get M dV dt, okay? To check the units. This is the same as summation of force equals to Ma, but write it down as I mentioned here with the impulse and momentum principle. So again, the answer here should be 5.66. Let's see what this problem is. So if 16 kilograms per second of water, so this would be the mass flow, okay? 16 kilograms per second, you see I put it here, traveling at 60 meters per second velocity, I put it over here, enters the turbine shown in the figure. Okay, so basically it means there is blades over here and it's going to be turning around, which has a 26 centimeters diameter and a blade angle of 120. What is the maximum power that can be generated? Okay, so this problem, if you do it in detail, the derivation is pretty long to find out, but I think they give you the equation here. So basically they give you the equation that the power is the volumetric flow rate times the density. And let's see what is V1 minus V. Okay, so I'm looking at this one, volumetric flow rate. Yeah, let's look at this equation here, volumetric flow rate, density, velocity squared divided by 4, 1 minus the angle, all right? So basically what I've done here, just substitute directly. This is the volumetric flow rate. Remember, rho equals to QA. So Q density here becomes the same thing as the mass flow. I wish here we go. I have the equation here. Mass flow equal to rho AV equal to rho Q. So basically this is AV is Q. So this will be rho AQ, okay? So this is really just M, all right? And then V1 is what we have over here. So we have the 16, 67 squared divided by 4, 1 minus the angle cosine 120. If you substitute directly into the equation, you get about 26,934 kilowatts or 26.934 kilowatts. All right. So again, I mean, like I suggest many times to you guys, the best thing over here to do is really, before going to the exam, is that you go through the book that they give you and post it on every single section of the book. So for example, let's say you have dynamics, but the one for the simple equation, and go first the exam and highlight the important equations. So what's important is that the day of the exam, you know where to go directly from the textbook or the booklet they give you to find the appropriate equations. problem number 13. What is the volumetric flow rate Q of water? And they give you the viscosity gamma 9.81 for the Venturi flow meter shown in the figure. So again, this is the Venturi. Like I was saying before, the Venturi effect. So this is like they do on the wind tunnel. If you turn the cross section here, the fluid is going to accelerate. So you see this one is different than this one. So this is exactly as a wind tunnel is designed. So let's see what is the volumetric flow rate Q of water. Okay, they give you the gamma for the Venturi flow meter here. All right. So again, you need to find the appropriate equation. The Venturi meters. Venturi meters is not that much used anymore because right now you have digital sensors. But for example, maybe you have seen in some of the aircraft, sometimes the aircraft have on their side like a little tube that way. It's a pitot tube. It's called pitot tube, which basically works as the Venturi effect. So if you look at the difference in pressure here, and if you calibrate it, it can give you, for example, the density, the velocity, or different aspects of the aircraft that you want to calculate. Again, this would be the Bernoulli effect. So if you substitute it over here just from this equation, direct application, CVA2 over here. All right, so let's see. The coefficient of velocity, was that given to you? Yeah, 0.83, A1, A2. So you have 0.83 times 0.015, which would be the A2, 1 minus 0.15, 0.102 square 2G times P1, 6,000. Gamma is the same, which is the 9,810. And now you have, so this one is this one, then you have P2, which is given to you to be 430 divided by the same gamma. So after this long calculation, you get that the volumetric flow rate is equal to 0.232. Okay, so that's generally all 13 problems that I cover for this course. But obviously, I give you about 4 or 5 minutes to cover each one of the problems. But in this video, I've done it everything at once. So that it's not going to last like the almost 2 hours that it does when we wait about 4 or 5 minutes between each one of the problems. So let me just pause this video, guys. And if you have any question, you can email me directly. And if needed, we can do another Zoom meeting to which I can answer any one of your questions. Okay? But as of today, I'm just going to stop the video here and I will post it in Canvas.